Hi, I'm Samir Desai, and in this video, we'll learn how a change in concentration will cause a system in equilibrium to shift.
You may have heard of the term homeostasis before. It's frequently used in biology to describe how our body changes to maintain an environment. For example, we like to state 98.6 degrees Fahrenheit. If our brain senses that we're getting too hot, it sends a signal to the glands to make you sweat and cool down. If we get too cold, a signal will be sent to our muscles telling us to shiver, thereby warming us up. Homeostasis is a great way to think about Le Chatelier's principle. A system wants to stay at equilibrium, but there are a couple of variables like concentration, pressure, and temperature that can shift this equilibrium. Le Chatelier's principle describes a phenomenon that counteracts these variables and maintains equilibrium. Let's use an example to understand how a change in concentration will cause a reaction to shift. Suppose we have the following reaction. Notice these arrows indicate equilibrium. Changing the concentration of either the reactants or products changes the value of Q, which is the reaction quotient. Q is equal to the concentration of the products over the concentration of the reactants. In this case, the reaction quotient would equal the concentration of C over the concentration of A squared times the concentration of B. Notice that we did not add the concentration of D into the reaction quotient equation. This is because we only take into consideration the concentration of gases and aqueous reactants and products in this equation, and did not use the concentration of pure solids or pure liquids. A reaction at equilibrium has an equilibrium constant, KEQ. We call it the equilibrium constant because KEQ will always be a constant value at equilibrium. In fact, K will equal KEQ at equilibrium. At equilibrium, KEQ and Q will be equal. But when we change the concentration of the reactants or products, then the value of Q will change and no longer be equal to K equilibrium. Let's take a look at how the value of the reaction quotient changing will cause a reaction to shift. We'll continue to use the same reaction example from before, which means we'll still have the same equation for the reaction quotient. When reactants are added or products are removed, then the KEQ will be greater than Q. So if reactants are added or we increase the concentration of the reactants, notice the denominator will be a larger number, meaning that Q will decrease. Similarly, if products are removed or we decrease the concentration of the products, then the numerator will be a smaller number, once again leading Q to decrease. When we add reactants or remove products, thereby causing Q to become smaller than KEQ, then the reaction will shift towards the product. When the equilibrium constant is on the left and the reaction quotient is on the right, I like to draw a line, creating an arrow. This right arrow reminds me that the reaction will shift towards the product. When reactants are removed or products are added, then KEQ will be smaller than Q. So if reactants are removed or we decrease the concentration of the reactants, notice the denominator will be a smaller number, meaning that Q will increase. Similarly, if products are added or we increase the concentration of products, then the numerator will be a larger number, once again leading Q to increase. When we remove reactants or add products, thereby causing Q to become larger than KEQ, then the reaction will shift towards the reactants. Again, draw a line creating an arrow. The left arrow reminds us that the reaction will shift towards the reactants. Let's use this information to predict how a reaction will shift when concentration is changed. In this question, we have a reaction in equilibrium, and we need to predict how the reaction will shift if we increase the concentration of H+. In relation to KEQ, will Q be larger, smaller, or the same? To help determine this, let's write out the equation for the reaction quotient. Remember that we only take into consideration gases and aqueous reactants and products. So Q will equal the concentration of the products, H plus squared, times HSO4 squared. This would normally be divided by the reactants, but solids and liquids are not accounted for, so this is the entire equation. Increasing the concentration of H plus means that Q will also increase. Therefore, KQ will be smaller than Q. Creating an arrow means that the reaction will shift towards the reactants. Using the same equation, we are now asked how adding solid lead will shift the reaction. We ask ourselves the same question. In relation to KEQ, will Q be larger, smaller, or the same? Again, taking a look at the equation of the reaction quotient we set up in the last slide, we don't see PB in the equation. So adding solid lead will not affect the value of Q in any way. Therefore, Q will continue to be equal to KEQ, and we would not expect to see any shift in the equilibrium. So there we have it. Predicting how a change in concentration will shift equilibrium is an integral part in understanding Le Chatelier's principle.